My name is Geunsik Lim. In this talk, I will present about the distributed compilation system to accelerate the software compilation with the open source like HTCondor and Distcc. I am working for mobile devices at Samsung company in South Korea. So here is outline. So first of all, I will introduce the motivation and background, and then I will explain our proposed system based on the open source like the Distcc and HTCondor. And then I will share our evaluation in real environment. And finally, I will conclude our experience and our proposed system. So the idle times of the distributed computers has increased steadily due to the computer uses and the generalization and the cloud computing. So, but the existing studies into the high performance computing still lack research of public computers facilities, which have a lot of idle times, as you can see. So we surveyed how many we can get the idle resource from the distributed remote desktop computers in real environment. So we surveyed the idle times and used times in real environment with the 300 dual-core desktop computer in university library. So as you can see, this picture means the worst case result. So we can utilize the 28% of the idle times. So, and then we analyzed the current status of the software size growth of the software for 4 years. So we selected the popular software like the Linux kernel and Android is called the software stack for mobile platform, and Firefox and Chrome is called the web browser and Chrome OS. So as you can see, for 4 years, we can see the Android mobile platform is increased about 7-fold. So at that time, we thought that we can reduce the entire build time of the mass software code if we can utilize the idle computers without any extension or expansion of the physical high-performance computing servers. So, and then we analyzed this picture shows the breakdown of the compilation cost when we tried to build the mass software code like the Android mobile platform. So you can see it. The compilation works to account for 67% of the total cost of the execution. So it means that the distributed related study and research is very important that we can reduce the entire build time of the platform source by utilizing the idle resource of the remote computers. So we planned we can utilize the idle resource for achieving the best compilation speed of the mass software code by utilizing the idle resource. So as you can see, actually there are a lot of idle computers during the power-on period. The first is printing server, and there are a lot of desktop computers in library or the companies, and some of the information quality system based on cloud computing technology. And there are a lot of desktop computers in university library and the hosting related service companies. So we believe that in unite, there is strength, like these pictures. So we designed the three major components to achieve our challenges. The first is the distributed compiler network to distribute the compiling task across the networks, like this picture. And second, the facilities that support the portable Linux system for the remote desktop computers. And third, the function that establish remote command line environment as a requirement in real environment. We could not use the GUI installer, as you will not be sitting in front of the distributed personal computers when users are trying to do their work. So we designed and implemented our distributed compilation systems based on the Distcc and HTCondor. So our proposed system consists of the three major components. As you can see, the first is the distributed server and client model to control the remote personal computer resource connected via networks. And second, the remote resource managed is called the dist-com manage for the scheduling the distributed PC resource. And finally, to support the heterogeneous CPU architecture for the target board, we recompiled the custom cross-compiler toolchain for the infrastructures. So you can see that the additional work based on the HTCondor and the Distcc open source. So I will explain about the three major additional our works. The first is the distributed server and client model. So the resource managers use the checkpoint restart mechanism to minimize the speed degradations, where the object files are the atomic level for checking point. To implement the proposed system, as I mentioned at the beginning time, I utilized the existing open source like the HTCondors. Actually, HTCondors support some of the features like this, collecting the information of the remote computer and the monitoring workload of the remote desktop computers. Actually, in real environment, we cannot modify easily some of the software component of the desktop computer because of the security and the polish. So, at first, we checked the remote PC status using the HTCondors, and then the user's client sent the command to compile the mass software code to the remote resource manage, and then the remote resource manage distributed some of the software code into the remote distributed computers, and then really the remote service daemon based on Distcc of the distributed computers try to compile or build some of the software code. So at this time, the minimal object is the atomic unit of the checkpoint restart to consider the consistency of the software code or the observable code. In the existing systems, actually, when we try to compile or build some of the code, the one object is handled by the one computer. So as we all know, in modern generation, we can utilize the multi-core architecture without a single architecture. So in proposed system, our object file based the server and client models executed by this multi-core aware mechanisms. As you can see, for example, if the object file is the two files, in this case, actually, this file is handled by the multi-core architecture. It means that the compilations, the unit depend on the number of the multi-core CPUs. So this page shows the controlling the remote PC resource by with our proposed system. Actually, to avoid the degrading the processing speed when the users try to work the sum of the PCs as the work period. In this case, actually, we designed the two mechanisms to implement the scheduling mechanism at the distributed computers. The first, we implemented the real-time priority related tasks to monopolize the CPU resource of the remote PCs when the users try to do not use any resource. And the second, we implemented the lowest priority of the scheduling as a time-sharing method when some of the users try to use the remoted PCs suddenly. In this case, we implemented our remote compilation, the service daemon is executed with the lowest priority, like the time-sharing schedulings, without the real-time priorities. So actually, to implement these mechanisms, fortunately, the Windows system and the Linux system support the real-time scheduling and the time-sharing scheduling. So it means that we don't need any modification to implement our distributed compilation system at the remoted computers. And then we considered about the task allocation and reallocation of the compilation task. So you can see we just considered about the task allocation and the reallocation by separating into the dedicated resource and shared resource queues. And in these queues, actually the minimal job unit is object files. So, and then we implemented the three state transitions of the task class: reject, state, and stop, and finish. The first, the reject status is used to deny the allocation of a task. And second, the stop phase, the stop status is used to break the allocation of the task to the remoted PC resource because the users access suddenly. And finally, the finish status is used to complete the running task normally. So, and then our proposed system supports the retry mechanism without migration mechanisms. So whenever compilation failure of the distributed computers occurs during the distributed compilation. So our retry mechanism handles the three cases. The first is the overload detection. If some of the queue more big than the CPU free, in this case, the resource managed by another idle computers. And second is task complexity estimation. And third is handling of the user access. So actually, as the further works, actually we have to consider how do we design and implement the migration mechanism more than the retry mechanism. So finally, we implemented the cross-compiler architecture for supporting the heterogeneous CPU architecture. So in this picture, as you can see the heterogeneous CPU mappers locations. So entirely, we implemented the cross-compiler architecture with the open source based cross-compiler architecture or the technology. So in this picture, the heterogeneous CPU mapper connects the source code up to the target machine code after recognizing the operating system. So we evaluated our proposed system based on the open source like HTCondor and Distcc. The upper fig show the screenshot of the parallel compilation, and below picture describes the screenshot of the distributed users client. This page shows the build time of the platform source when we try to build the mass software code like the Android mobile platform. So as you can see, in the existing system, we needed the 51 minutes to build the Android mobile platform 4.2.2. So, but when we adjusted the distributed compilations, based on the open source, we reduced the build times from 51 minutes to the 80 minutes. And then the below picture shows the breakdown of the build time cost. So from our analysis, the 25% is consumed by the network speed, and 30% is consumed by the computing power of the remote PCs, and 45% is consumed by the CPU scheduling method, like the dedicated resource scheduling or the shared resource scheduling.
How many machines?
Like
700 machines or something?
We assigned the 9 machines among the 100 remote PCs. Yeah, you can see the allocated the 9 parallel compilation queue like this. Yeah.
Okay, thank you.
And this page shows the compilation speed with the remote personal computers. In these pictures, the less is better. So among the 300 remote computers, we allocated the different available PC resource, like please see the x-axis 5, 10, 15, 20, to more than. So we got the reasonable result from our experiment, but please see the red rectangle here. Ideally, the performance of the 10 machine will be similar to the 10 core PCs, but from our experiment, the performance of the 10 machines was similar to the 8 core PCs because the network speed and low computing power of the remoted PC is different. So we lost the sum of the performance. And please see that this the right red rectangle. This result shows the difference between the shared resource scheduling and the dedicated resource scheduling. The compilation processing performance of the shared resource scheduling method largely depends on the CPU usage of the remote PC computers compared to the dedicated resource scheduling method. At the beginning time, I mentioned when we adjusted the dedicated resource scheduling, actually we can utilize the maximum of the CPU resource of the remote computers when the users will not use any resource, for example, after work time or after the curriculums in the university. And we also evaluated the effectiveness of our proposed system on the cloud computing related environment. So the proposed system is as effective as one high-performance code computers, including the 40 core. As you can see, this picture shows the good result of our proposed system. The less is better than in this picture. Actually, in our proposed systems, we adjusted some of the guest OS on the virtual machine based on KVM. And then we ran the native OS at the high performance computing powers. Like these high performance computers is consist of the 40-core Intel Xeon E7 process and 32 gigabyte memory. So, but as you can see, we lost the 3-minute difference in performance. From our analysis, we figured out the performance loss is caused by the emulation operation of the KVM virtual machines. And finally, we evaluated our proposed system by adding the C cache to speed up the recompilation. This page shows the effectiveness of our experiment using the C cache. The C cache effect using the dedicated resource scheduling is correlated with the memory shortage of the desktop computers and with the physical memory capacity of the cachings. So at that time, we expected that we could get the high performance by using the C cache, but as you can see, we got the small benefit with the C cache because, as I mentioned, the memory shortage and the physical memory capacity of the caching. So this page showed that we summarized the comparison between the existing system and our proposed system. In summary, our proposed system is based on the Distcc and HTCondor. What is the difference compared to the existing system? As I introduced our additional chart, our system supported the multi-core aware object-based unit and the retry mechanism for the checkpoint restart technology. And we also handled the shared resource scheduling compared to the Distcc. So we designed and implemented our proposed system as a hybrid system compared to the existing system. So we surveyed and reposed to some of the paper and the open source. Yeah, let's conclude our experience and technology. At the beginning time, as I mentioned, either computer resource connected by the network are more ubiquitous than ever before. For example, cloud environment and BYOD is called the bring your own devices and the generalization of the computer usage. And so we designed and implemented the distributed compilation system based on the open source like HTCondor and the Distcc. And we, from our various experiments, we figured out our proposed system is usable for the drastic improvement of compilation speed using the existing idle PC resource without any expansion of the physical computing power. Yeah, thank you for your attention. Yeah. Yeah.
The PCs that you were using the idle time of, were they slow to react when someone wanted to go and use them?
Yeah, actually, I think that we needed various evaluation to verify the effectiveness of our proposed system. And as so the evaluation, actually, in the real environment, we evaluated the physical the limitation. For example, we know that we cannot utilize the idle speed of the network in real environment. And the overall, okay, I also have to think how can I improve and overcome the limitation of the retry mechanism, as I explained about the retry mechanism. So I mean that as a further works, I needed more times. And
I'm not sure, was it noticeably slower?
Sorry, why is it slow?
Like if someone wanted to use a PC, did it take a while to stop compiling?
Yeah. About the start compiled by users?
So
or, yeah.
If I may, a user walks in, the machine's currently in shared resource mode, it's got a compiler happening. How long from them moving the mouse before it reacts and the compiler goes away and they get full use of the machine? What's the latency?
Yeah, just a moment.
And did the users notice? I guess that's really the...
Yeah, it wasn't noticeable. Did it provide a detrimental user experience?
From our experience, until now, we consider the different the CPU scheduling, like the shared resource scheduling for the user experience. When the users try to interrupt the desktop computers. So I introduced two scheduling mechanisms like this.
So sorry.
Yeah, here.
Dedicated one.
Yeah, here. So, okay, from our experience, actually we could utilize the existing platform like the Windows and the Linux, as I mentioned, because fortunately these two operating systems support the two different the scheduling methods, like the real-time priority and the time-sharing method. So, but in the future, we have to consider like this, the Solaris or the VxWorks. Actually, the VxWorks is just only the real-time operating system. It means that this operating system does not support the time-sharing method. So we have to think or the study about the another operating system. Yeah. And wait. Yeah, currently. Anyway, we will open our additional work after the stabilization of our system and after the approval of my boss, because I am working for the mobile device at Samsung company. Yeah. Any question? Yeah.
Are you building just the kernel or the whole Android system?
You mean that can we utilize this proposed system at another system without the Android? Yeah.
What are you building? Are you building just the Linux?
We tried to build the entire Android mobile platform, and as you can see, the Linux kernel. Okay, and additionally, you can see it, the compilation status of the Linux kernel. But from our experience, although we support the stable, the cross-compiling infrastructure, but to compile the source code for the target board, we have to modify the trivials of the Linux kernel to compile, to support the distributed compilation. But this is just the engineering issue. Yeah. Okay.
Thank you very much. Yeah.
Thank you.